everybody. Good morning. Welcome to the BRE 600 two-stage sour water stripper webinar. Just really quickly, I wanted to remind everybody that, we as a company are really here to support our customers. We sell process simulation software, ProMax, obviously, but we want to make sure that all of our customers are really supported and really have everything that they need to accomplish their objectives and solve their problems. So if you're not aware, we offer free training and free technical support along with every license of ProMax. And if you're not using it, then you really should. We have an entire team of chemical engineers in our technical support group who are basically on staff for one reason, which is to help you solve your problems using ProMax. So please, feel free to reach out to us anytime you need for help with anything. We're here for you. And that's the reason that we opened our office in the EU. So right now we have a small satellite office in the European Union. We're located in Brno, Czech Republic. I'm responsible for the kind of running the day-to-day operations of the office. My name is Lucas Garfield, so you can see my picture down there on the bottom. And I have two colleagues with me, Václav and Katerina. And together, the three of us are responsible for helping all of our customers in Europe. So if you ever need anything at all, just get in touch with one of us and we'll be really, really happy to help you with your project, with your simulation, whatever you need. Today, we're going to be talking about two-stage sour water strippers. And what I'm going to do is I'm going to show you how you can build your own two-stage sour water stripper simulation from scratch. Now, we're going to start with a very simple process description taken from the book Gas Purification by Colin Nielsen. And we're going to just build the simulation and kind of start exploring it. We're probably not going to have time to do very much optimization today. And then another topic that we can talk about is ammonia purification, because as we'll see, what we do in a two-stage sour water stripper is we end up producing a pure or nearly pure ammonia stream. But in order to make sure that we meet the specifications on that ammonia stream, some purification is generally required. And that purification step, it can be quite complicated. It's something that really needs quite a bit of time to discuss and develop. So it's a really good future webinar topic. So we'll plan on having webinars where we continue to work on this unit. Now, today we're going to assume that you generally understand what's happening in a sour water stripper. But just so that we're kind of starting on a level playing ground, let's say, the idea here is that we have a stream of sour water, and it's sour because it contains H2S and ammonia. And what we'd like to do is we'd like to treat it. We'd like to remove the ammonia and the hydrogen sulfide. And we do that in a stripper. And its overhead, the stripper's overhead, is typically taken and sent to a sulfur recovery unit. And then the stripped water can be used in different places throughout the refinery. There are lots of sources of sour water. Most units in a refinery are going to be producing some sour water, even distillation columns, because if you think about, for instance, a crude distillation unit, you're using stripping steam throughout the entire column, and then the condenser is removing that water, and all of that water is going to end up going to a sour water stripper. If you think about your desulfurization units, those are producing a large amount of sour water that contain ammonia and H2S in them. And so we have to treat all of that water. Usually the specification we're trying to meet is something in the range of 50 parts per million ammonia and 10 parts per million H2S. And I've put parts per million ammonia, the 50 ppm ammonia, in bold here. And the reason for that is because, practically speaking, H2S strips much more easily than ammonia. It has a higher vapor pressure. And so usually the ammonia specification is the one that we need to try to meet. Once we meet the ammonia specification, in every case I've ever seen, you're guaranteed to meet the H2S specification. There is another way to do this, where we actually use two columns. This process was originally developed and licensed by Chevron, and they called it the WWT, wastewater treatment process. And that process is now licensed by Bechtel. And the idea is that you can have two columns and produce two separate streams, a purity H2S stream and a purity ammonia stream. When this was originally being marketed and developed, it was very beneficial because in previous generation sulfur recovery units, there was a problem with ammonia destruction. The burners didn't operate at high enough temperatures or with long enough residence times to guarantee ammonia destruction. And ammonia can be a big problem in a sulfur recovery unit. So there was a huge benefit to being able to separate those two streams, because it meant that you could send a pure H2S stream to your SRU and not have to worry about all the problems that ammonia could cause there. Nowadays, it's possible to get burners for sulfur recovery units that do have high enough temperatures and long enough residence times to destroy ammonia, but there's still good reasons to think about employing one of these units because, first of all, if you're putting in a new sour water stripper at a refinery, there's no guarantee that you're sending the overhead stream to a modern SRU. Maybe the SRU is due for a revamp, but still has one of those old burners. The other thing that this process gives you is a lower total flow to the sulfur recovery unit. So perhaps it could help with debottlenecking, because you'll have less, if you don't send the ammonia to your sulfur recovery unit will have a lower hydraulic load. And then finally, there's also the potential to produce a saleable ammonia product. So we can take that ammonia and we can produce anhydrous ammonia or aqua ammonia, and we can actually sell that ammonia perhaps to the fertilizer industry or to whoever's willing to purchase it. So here's a basic process flow sheet from ProMax, and this is just taken from one of our built-in examples. And you actually have access to this simulation, by the way, if you've got ProMax installed on your machine. So even though we're building the simulation from scratch today, if you were actually to start with one of these, you wouldn't necessarily have to do that. Although I think it is a useful and instructive thing to do, which is why we're doing it. But I'll show you how to access this example towards the end, so that if you need to get it on your own, you can. And just really briefly, before we kind of dive in, I want to remind everybody that when we're talking about sour water stripping, we need to think in terms of the electrolytic chemistry that's happening. Hydrogen sulfide acts as an acid. So when H2S dissolves in water, it dissociates into the bisulfide ion. And then that bisulfide ion, HS minus, it can further dissociate into sulfide, S2 minus. Ammonia is a base, and so ammonia can accept a proton to form ammonium. And if you think about it, we typically have H2S and ammonia present together. And because one of them is an acid and one of them is a base, they have this effect of where they hold on to each other. So that's just something to keep in mind as we work through this, is that electrolytic chemistry is going to play a really big role. Now, we're not really going to necessarily notice it ourselves. ProMax is going to take care of everything behind the scenes for us, but just be aware that this chemistry is present, and ProMax is rigorously accounting for it. Now, this process, as I said, it was developed by Chevron. It's currently licensed by Bechtel. There are a few different sources that you could look to if you wanted to get an idea of how one of these units would run. And the one we're going to use today the reference we'll use today is the book Gas Purification, the 5th edition. This is by Colin Nielsen, and this is kind of like the Bible of the gas treating industry. So I've got here a snippet. This is the flow diagram that Colin Nielsen give us, where they describe the process. And you can see that the process is not particularly complicated. Our sour water comes in. It goes to a degasser. That's where we release inerts. The sour water is stored in a feed tank. And then it's sent to a hydrogen sulfide stripper. So the H2S stripper, it creates a pure H2S product. And you can see here that they tell us it should have less than 100 ppm weight ammonia. And if you read through the text, they tell us that the typical operating pressure of this unit is about 100 psig, 100 pounds per square inch. That's about 7.5 bar. And they tell us that a typical overhead temperature is about 100 degrees Fahrenheit, which is about 40 degrees Celsius. Now, the bottoms of that first column go to a second column, an ammonia stripper. And here we're told that the typical ammonia specification is about 50 ppm weight in the stripped water. And we're told that the typical pressure is about 50 psig, which is about 3.5 bar. And that's really all of the information that we're given in the book Gas Purification. It's a fairly light process description. It's not a lot to go on. But that's what we're going to go on today. We're going to take that very, very basic design information, this idea that the H2S stripper operates at about 7.5 bar, that the ammonia stripper operates at about 3.5 bar, that we want 100 ppm weight ammonia in our H2S product, that we want 50 ppm weight ammonia in our bottoms product. And we're going to see if we can just get this simulated and developed ourselves from that very, very basic information. Now, one thing that we have to do with the ammonia stream, if we do want to produce a saleable ammonia product, it will still have quite a bit of H2S in it, as we will see later. And so there is some further treatment that's typically needed. If you want to produce ammonia vapor to send to an incinerator that has less than about 1,500 ppm weight H2S, keep in mind we're talking about the purity ammonia now, you typically need one stage of scrubbing, so water scrubbing, that's shown here. If you want to produce a saleable ammonia product like anhydrous liquid ammonia or aqua ammonia, you typically need two stages of scrubbing. So a first stage where you have wash water, and then a second stage where you scrub with caustic. Now, we're not going to discuss the ammonia purification in depth today, but I think it would be a very good future webinar topic, because the interesting thing that occurs here, it's not shown in this diagram, but the bottoms of those scrubbers get recycled to the process. And practically, the sour water stripper unit and this ammonia purification unit, their operations are very, very tightly coupled. And it's a very, very interesting and complex system. So like I said, I plan on developing another webinar where we really dig in and go into depth discussing how this works and how it integrates with the sour water stripper. So be looking for that. And then Colin Nielsen give us some again, these are just some typical product specifications for what we can produce with this process. So that was our brief introduction. And now what we're going to do is we're going to go ahead and just try to construct one of these units. So we'll start with a blank flow sheet, and I'm going to walk you through how I would do this. Now, the first thing I do whenever I'm simulating a new process is I set up my environment. So that's where we choose our thermodynamic package and the list of components that we'll be using. So to do that, I'm going to click up here on Active Environment. And we need to remember that we need to use a thermodynamic package here that will account for those electrons or those electrolytes that we're going to have in the solution. So we're going to use this electrolytic ELR PR package. And one of the ways that you can figure out what property package to use in ProMax if you're not sure, if you right click on any of these package names and select what's this, a pop-up comes up and it gives you some advice. Here, I'm told that for sour water stripping, I should use the electrolytic ELR, that stands for Extended Long Range Package, and so that's what I'm going to use. And then I need to set up my component list. So I'm going to click here on Components, and I'm just going to go ahead and add water, ammonia, and H2S. Now, other common contaminants in sour water are hydrogen cyanide and phenol. And those are present in ProMax, and they dissociate and act as acids like they should. So if you have those in your system, you can definitely include them. We're just going to leave them out today to make things nice and simple. And I'm going to click OK here. So I've got my environment created. I'm ready to start simulating. And the place I usually start is at the beginning. So we'll go ahead and take a process stream, drag it out into the flow sheet, and we're going to call this our feed stream. Now, we need some basis to work from today. I'm just going to go ahead and open that feed stream, and let me change the units here to kilojoule bar. We'll assume that this comes in at 40 degrees Celsius and that it's at basically atmospheric pressure. We'll say that this is coming from that storage tank and that it's at atmospheric pressure. We need a flow rate to work with. We'll just assume 100 cubic meters per hour today. And then we need some kind of sour water basis to work from in terms of composition. So I'm going to click here on the composition tab. I'll double click to open my composition specification window. And then on a mass basis, we'll say that this is 96.6% water, 1.5% ammonia, and 1.9% H2S. I now have a temperature, a pressure, a flow rate, and a composition present, and so my stream solves automatically, it turns green. And one thing that I happen to know is that the feed is almost always going to be preheated by contacting it with one of the hot streams available in the process, one of the reboiler bottoms. So I'm going to go ahead and right off the bat, add a heat exchanger. And this is a single-sided heat exchanger for now, but we'll end up connecting this to the other side later on once we add a column that actually has a bottoms stream we can connect it to. And in this heat exchanger, I'm going to go ahead and go to process data. I'll set a pressure drop of 0 bar, and I'll set an outlet pressure of, let's do a guess of 100 degrees Celsius or perhaps 99 degrees Celsius as a starting point. And then the other thing that we should do that I forgot, we probably actually want to have a pump upstream of this heat exchanger. So let's add that. So I'm going to drag a pump out onto the flow sheet, connect the pump to that exchanger, put an energy stream to my pump. And then on my pump, what I'll do is I'm going to go to process data. I'll put in an efficiency of 65%. And then I'll put a discharge pressure at the outlet. Now, Colin-Nielsen, or the reference we're using as our starting point, specified that a typical pressure for the H2S stripper is 100 psig. So I could type in, let's say, 100 psig here, and then delete my psig specification to go back to bar. It's about 7.9 bar. So that's what we'll come in at. And maybe we'll come in just a little bit higher so that we can, account for a pressure drop in the exchanger, etc. I'd set a pressure drop here of 0 bar, but we can maybe increase that to be a little bit more realistic. And at this point, we have our preheated feed stream. So we would want to take this and send it to a column. So let's go ahead and get a distillation column out onto the flow sheet. I'm going to go to my distillation columns, and we're going to drag out this one. This is a distillation column that has a reboiler attached. We're not going to include a condenser yet, because typically what we do with a 2-column sour water stripper is we use some wash water instead of a condenser on the first H2S stripper. Now, right now, this block is red. That's because it doesn't have all of its connections. And what I'm going to do is get this kind of set up. We've only got 2 stages here, so I'd like to add some stages. And then we're going to need to add the overhead outlet, and we're going to need to add the bottoms outlet. If I double click into the column and I go to the process data tab, well, actually first in the connections tab, I'm going to go ahead and add some stages, and we'll just start with 15 stages today. And we'll use the ideal stage model because it's going to make things just a little bit simpler for us at first during these early iterations. 15 stages is kind of arbitrary. That would be something that you could perhaps optimize later on, but for now, we'll just take 15 as a basis, as a starting point. And I know that I'm going to want to have a water wash above the feed. So I'm going to go over here to the process data tab, and then I'm going to click here on stages. And what I'll do is I will go ahead and check mark this box, show stage, next to stage 3. And it's going to show stage 3 so that now I can connect the feed there. I'm also going to create a small pressure change here. We'll say maybe 0.3 bar throughout the column. And I'm going to connect this feed here. right into stage 3. Now we'll need some wash water if we want this column to solve. In ProMax, in ProMax you always have to have a feed to your top tray to get the simulation to solve. So I'm going to take a process stream, add it here, and we'll call this wash water. And we'll eventually get this connected to the rest of our system, but at first this is just to get the first column going. And we'll go ahead and double click on our wash water, and let's go ahead and just say that this is at 40 degrees Celsius. We'll say that it's at 8.5 bar. That's what we had our pump come out to. And then we'll say that the standard liquid volumetric flow rate for now is just 1 cubic meter per hour. If you remember, we did 100 cubics for our feed, so that's about 1% of the feed flow rate. And then for the composition, for now, we'll say that this is just pure water. So at this point, the column has both of its feeds, but it's not quite ready to solve. And one way that I can tell that it's not quite ready to solve is because I still have some red streams down here. Red in ProMax indicates that the stream does not have enough information to solve. And the problem is, if I open the column, I haven't actually done anything to specify what the duty ought to be, what the duty of this stream Q3 should be. What we'll do is we'll go here to the specifications tab and we'll set that up. But before we do that, one thing I forgot to do previously, we set our pump discharge to be about 8.5 bar, and we did the same with our wash water. But I would actually like to carefully control the column pressure myself, and I can do that by setting the pressure on one of the stages. In this case, I'm going to go here to stage 1, and I'm going to override the default stage pressure. Right now, ProMax is populating this stage pressure based on the pressures of the 2 streams that are feeding the column. But I can override that as if there were something like a pressure controller on the overhead. And I'm going to say that I want this to be 100 psig, again, because that's what's recommended by Cole Nielsen. And then I'm going to go back to bar so that we're in units that we're a little bit more familiar with. And we see that we're at 7.9 bar on that top stage. So now I'm going to go to the specifications tab, and I need to put in a duty here. And, truthfully, I'm not really sure what that duty ought to be. In cases like this, there's a few things that you could do. The first thing that you could do would be to go to a rule of thumb. And there are a lot of rules out there, rules of thumb out there that you could look at that would tell you, you need typically this many kilograms of steam per cubic meter. The other thing that you can do, if you can't find a rule of thumb, is you can use the boil-up ratio. The boil-up ratio is not something that people necessarily discuss a lot outside of the realm of process simulation, but it's kind of like a reflux ratio applied to the reboiler. It's a really nice specification to use when you're working with columns in a process simulator because it's kind of the, let's say, natural solution to the column algorithm. Columns tend to solve very easily when you specify boil-up ratios. So I'll just show you, if I come in here and I put a target of say 0.1 as my boil-up ratio, and I click specification, I'm now ready to go ahead and solve this column. And I could click execute here, and the column solves nicely for me. And the next question that I have is, how well is this column working? Am I stripping H2S and recovering ammonia into the bottoms, or what's happening? So let's start doing some investigating and see how well this is working. Now, how might we do that? What might we want to look at? Well, here on the Process Data tab, I can go to Recoveries, and I can see that right now, into stream 6, which is my bottom stream, I'm recovering 100% of my ammonia and 33% of my H2S. And I can see that into my overhead stream 5, I'm recovering, of course, about 66% of my H2S. So that's pretty good for a first attempt. Now, what we'd like to do is to get this column working a little bit better and perhaps see how much greater we can increase that H2S recovery without negatively impacting our ammonia recovery. And then the other thing that we'd like to think about is what temperature is this overhead stream 5 at? Are we close to that 40 degrees Celsius that Colin Nielsen pointed out as a typical operating point? And are we on spec in terms of the ammonia content? So if I open up stream 5 right now, let's just take a look at that ammonia content. We know that we're supposed to have 100 ppm weight ammonia or less in this stream. So if I go to the composition tab and we go to mass fractions and I put that composition in ppm, right now my ammonia content is 0.007 ppm. So I've got a little bit of room here. I could probably safely increase my boil-up ratio, in other words, increase my reboiler duty, and still meet my ammonia spec, but increase my H2S recovery. So that's what I'm going to investigate next. And as we start working on this column, it's going to be really useful if we can get access to all the information that we're interested in from one place. What I like to do is here in the specifications tab, I'm going to add specifications for all of those different performance indicators so that they're kind of collected all in one place and I have access to them and I can really quickly, and it's going to really help facilitate the kind of iterative exploration that we want to do. Let's start adding some different interesting information here. And some of this specifications that I want to create now are just going to replicate information that we can find in other places. But again, like I said, I just want to gather everything in one place. So let's click add, or I'm going to click add. And the first thing I'm going to add is a recovery specification. So I can do this component recovery, and I want to look at the NH3 recovery. The NH3 recovery, that's the ammonia recovery. So I'm going to say that the component I'm looking at is ammonia. And I'm interested in the recovery into the bottoms liquid, okay? So right now, I can see that there's a value of 100% there, which is good. That matches the recovery we looked at earlier. And now I want to create an H2S recovery specification. So I'll click add, and then we will do another component composition, and we'll say H2S recovery. Here, we'll choose H2S as our component. The only difference is that we'll choose stream 5 as a recovery stream because we're interested in the H2S recovery into the overhead. And I actually just noticed I selected the wrong specification, so I'm going to click cancel and actually delete this. Add it again, and I need component recovery. That's what I should have done. So I'll do H2S recovery. And again, this is going to be into the overhead stream. We're looking at H2S, and there's our 66.7 recovery. So the question is, can we get this number to increase, but keep this ammonia recovery nice and high? And how would we do that? Well, one thing that we could do is we could think about increasing our boil-up ratio a little bit. That would increase our reboiler duty. If I went from, for instance, a boil-up ratio of 0.1 to 0.12, I see that my ammonia recovery is still at 100%, but now I've got my H2S recovery up to 75%. If I increase my boil-up ratio to 0.13, I'm getting an ammonia recovery of 100, an H2S recovery of 80. So let's keep pushing this and see how high we can go. This is kind of an interesting thing to explore. We're increasing the reboiler duty, and we're watching what happens in the column. Now, I went up to 0.15. I was at 0.13 and the column was solving. I went up to 0.15 and the column failed. And the column is now pink. Pink is a new color in ProMax 5.0 that indicates a failure. And if I look down here in my message log, I get this warning that says, the outer loop numerical method failed due to the error maximum number of iterations reached. So for some reason, my column is now having trouble converging at this higher boil-up ratio. Now, there are a couple of things that I can do here, and this is a fairly common occurrence when you're working with distillation columns, particularly strippers, including amine strippers, but also sour water strippers. And one of the things that we can do to help us get the column to converge is go to the convergence tab, and we can think about changing either this enthalpy model or this inner loop model. And what I'm going to do is I'm going to change this inner loop model to Boston-Sullivan non-ideal. And I'm going to try re-executing the column. And I see that now the column works just fine. So this is one tip that I can offer you, is that when you're working with sour water strippers, sometimes it can be useful to play with these two settings. Now, as far as what these actually do, they adjust the algorithm that the column uses. They will not change the final results. They only affect the algorithm. I personally can't really tell you how they change the algorithm myself. If you want to dig into it, you can right-click on them, choose what's this, and there's a long description that we give you about what it does to the column algorithm. But the advice I'd like to give you today is try changing these. There's only 4 possible combinations, so it's not hard to iterate through all of them. And then if you still can't get your columns to converge, just email it to our technical support team, to me or to Václav, to Katerina, to support@bearea.com, and we'll help you. But in this case, our column is now working really well now that we're using this Boston-Sullivan non-ideal option. And if we go back to the specifications tab, we see that at this boil-up ratio of 0.15, we're now getting a 99.3% ammonia recovery. Our H2S recovery is up to 93.4%. So that is a good H2S recovery, but our ammonia recovery has suffered just a little bit. So the next question we have, or I would have, is this a problem? Is that an acceptable ammonia recovery? Well, let's check and see what the ammonia content in the H2S is. And we'll do that by adding a specification instead of looking in the stream directly. So I'm going to click here on Add, and now I'm going to add a component composition. We'll call this NH3 in our H2S, so that's an impurity. And we're going to say in stream 5, I want to see what the mass fraction of ammonia is in ppm. And I see that the ammonia content in my H2S stream is now 4975. That is greater than our 100 ppm specification. And I'm going to go ahead and type in a value of 100 here in the target column, just to remind myself that that's what I want to look for. But keep in mind that at this point, we're not actually controlling the column using the specification. We're still controlling the column using the boil-up ratio. So what I would need to do here is probably either think about backing off on my boil-up ratio or increasing my wash water flow rate. To back off on this, I might decrease the boil-up ratio to 0.14 and see what happens. At a boil-up ratio of 0.14, we're able to get an 85% H2S recovery, and we're on spec. When we go up to 0.15, which is where we were previously, we're now off spec on our ammonia content. But perhaps what we can do is increase our wash water flow rate a bit to knock that ammonia back down into the column, but still give us a high H2S recovery. So let's try that. Our wash water was at 1 cubic meter before. Let's try increasing the wash water flow rate to 2 cubic meters per hour. So if we go up to 2 cubic meters per hour, that has helped a little bit. We now have 1,000 ppm ammonia in our H2S, so that's less than we did before. We still got that high ammonia recovery, or high H2S recovery, and our ammonia recovery is increasing a bit. So we could keep trying to increase our wash water flow rate here. Let's try to go to 3 and see what happens. Okay, at a wash water flow rate of 3 cubic meters per hour, now our ammonia in our H2S is at 53 ppm, which is very close to the specification, but looks quite good. Our H2S recovery is 93.4%, which is pretty good, and our ammonia recovery is 99.99%. So that looks really good. And then let's add one more specification here. We'll click on phase property, and let's just take a look at what the overhead temperature is and see if we're in line with those guidelines that Cole and Nielsen gave us. So we'll choose stage 1, and we'll take a look at the vapor phase, and we'll choose the property temperature. And we see that the temperature here is 91 degrees Celsius. We're actually operating at a little bit higher temperature, perhaps than what Cole-Nielsen recommend, but at this point, we're getting a very good both H2S recovery and ammonia recovery, and we're producing an on-specification H2S product. So let's go ahead and continue with this. The next thing that we would want to do is to start thinking about adding that second stripper. So let's add our ammonia stripper next. I'm going to go over to my distillation columns, and now what I'm going to do is I'm going to bring out a distillation column that has a partial condenser and a reboiler attached to it. We'll go ahead and set this column up. Again, we'll use 15 stages here. Not a whole lot of thought going into the number of stages that I'm putting. This is kind of just a basis to help get us started. I'm going to say that the condenser is, we'll say that we've got 2 stages for wash below the condenser, so we'll feed to stage 3. We'll say that the top stage pressure is 50 psig, since that's what Cole-Nielsen recommends, and we'll take that back to bar, so that's about 4.46 bar. And then we'll say that we've got a pressure change here of about 0.3 bar. We'll go ahead and connect this together. So we need to add an overhead stream. We need to add a bottom stream. And now we need to configure this column. We need to tell it how the condenser should operate and how the reboiler should operate. So let's go ahead and open that column. We will go to the specifications tab. And what I'm going to do here, I'm going to go ahead and add a specification so that we can control the condenser temperature. Under type of specification, I'll choose phase property, and we'll say condenser temperature. For the stage, we'll choose condenser. For the phase, we'll choose vapor. For the property, we'll choose temperature. And Cole-Nielsen didn't actually give us any guidance on this, but a common rule of thumb is to operate at no less than 85 degrees Celsius to avoid the formation of ammonium sulfide salts. And so that's what we'll do. We'll say that the target temperature here is 85 degrees Celsius. And I'm going to activate that specification by just clicking on its radio button here. And you see when I do that, the streams around the condenser, they all turn brown, indicating that that degree of freedom has been occupied, that these streams are ready to solve. And now I need to specify how I want this reboiler to operate. And so I'm going to start kind of like I did before. I'm going to set a boil-up ratio here, and I'll just choose something like maybe 0.15, activate that specification, and then see if I can get this column to solve. And the column solves fine. And now that the column solved, the next question I have is, how is my performance? And the key performance indicator here is going to be how much H2S do I have in my stripped water, and how much ammonia do I have in my stripped water. So let's go ahead and add specifications for those. I'm going to click Add, and the type of specification that we'll choose will be a component flow composition, and we'll say H2S in stripped water. Again, I could check the stripped water stream itself for this, but it's just nice to have everything in one place. And so we're going to stay from our bottoms liquid on a mass fraction basis in ppm. How much do we have? And we've got 22 ppm of H2S right now. So that would be off specification if we had a 10 ppm specification, but it's close. We're at a point where we can work with this. Let's go ahead and see what our ammonia would be. So we'll do NH3 in our stripped water. We'll click OK. Again, our stream here is going to be bottoms liquid, and then we want to look on a mass fraction basis, how much ammonia do we have? And we see here we've got about 480 ppm. So to fix this, I could increase my boil-up ratio, right? I could just strip a little bit harder. So I could come in here and I could say perhaps, 0.18 as a boil-up ratio and execute this. Now I see I've got my NH3 in the stripped water down to 77 ppm, and I could keep adjusting the boil-up ratio. Another thing that I could do is I could try to just control based on that ammonia specification myself. So I could come here and I could say I want that ammonia to be 50 ppm, and I could disable my boil-up ratio, and I could say control the column such that the ammonia in the stripped water is always going to be 50 ppm. So let's execute this. I can actually solve the column like that. So now I'm always going to meet the specification. And this is something really useful to have on this column, because on this column is going to have different compositions coming in depending on how we operate the first column. And so if we're working on this process and we're kind of iterating on different process parameters, if we're making changes here, we would like for this column to always give us guaranteed performance. And when I say guaranteed performance, I mean we'd like to guarantee that we always meet our stripped water specification. And that's what this will do for us. So now we're meeting our stripped water specification. Let's check and see what our H2S content in our overhead stream here, stream 11, is. I'm going to add another composition specification, and we'll say H2S in overhead. We'll take a look at the distillate vapor stream, and we'll look at what the mass fraction of H2S is on a ppm basis. And it's 70,000 ppm right now. So that's quite high. If you think about it, when Colin Nielsen was discussing the H2S content of the ammonia streams, they were suggesting that we should have, for anhydrous ammonia that's destined for incineration, about 1500 ppm. There's a lot of H2S in this ammonia. What we would need to do to remove it is to go through those wash stages, to go through those scrubbers. Let's table that discussion for the moment and then finish building out this simulation, and then I'll just we'll circle back to that. One thing that I'd like to go ahead and do is take into consideration where the energy from this preheater is coming from. And a good place to take that energy from would be this stream. If I look at the temperature of stream 12, this is at 150 degrees Celsius, so I've got plenty of energy here, and I could use this stream to do my preheating here. I'm going to go ahead and add in another heat exchanger. And these are both single-sided heat exchangers. I'm going to put in a little pressure drop here. We'll say 0.3 bar. But I can actually connect this energy stream to this heat exchanger, and this is now going to function for me like a two-sided exchanger. And so that, I can see, takes my second stripper's bottoms from 150 degrees Celsius down to about 90 degrees Celsius. And it's possible that we would want to do some further cooling here. So perhaps we'd want to add an air cooler and take that down to something more sensible like 40 degrees Celsius. So I do that just by adding an air cooler, setting the outlet temperature to 40 degrees Celsius, going and putting in a small pressure drop. And now what I could do is I could actually start to discuss where this wash water stream comes from. This wash water stream is actually probably going to be a recycle from our stripped water. So let's go ahead and add in a splitter and set that up. I'm going to move everything over to the left just a little bit. Just going to rearrange these a little bit so that they are nice and neat. Oops, I grabbed the wrong one there. That's okay. Okay, that looks good. Now what we're gonna do is we're gonna take this and recycle it to be our wash water stream. Now we're gonna need to add a pump to do that. So I'll go to fluid drivers and we'll go ahead and put a pump out onto the flow sheet. I'll give that pump a discharge pressure. We'll use 8.5 bar. That's kind of what we've been using for everything. And we'll need to put an efficiency in on this pump. And right now we're using a flow rate of wash water of 3 cubic meters per hour. So I'm going to come back here to stream 16. And in stream 16, we'll go ahead and say that the flow rate is 3 cubic meters per hour. And let's solve that. And now I'd like to go ahead and just take this and replace my wash water stream with it. Now the challenge I'll have if I do that and I click execute flow sheet, at this point nothing will solve. And the reason for that is because in order for a column to solve, all of its inlets need to be solved. And this inlet can't actually solve until this column solves. So what I need to solve this problem is to use a recycle block. I'll drag a recycle block out on the flow sheet. Recycle blocks in ProMax allow us to provide an initial guess in these kinds of loops. And I'm just going to use that wash water stream that I had previously on the column as my initial guess for what the wash water loop is going to be. So I've got my recycle here. I'll just hook this back up. And now let's go ahead and solve this. It's going to iterate through a few times. The only difference now is that my wash water does have just a little bit more ammonia in it. So let's go ahead and open our H2S stripper back up and see if that affected us. It looks like no, we're still on specification. We're looking quite good. We could add some callouts to our flow sheet to help really demonstrate that we've got this unit operating properly. So I could put a call out here, for instance, and I could display perhaps the H2S content. Okay, and I can change my number of significant figure. Well, actually, I'm sorry, I did H2S content. What I meant to do there was ammonia content. So I can show the ammonia content in ppm. And I can also show the ammonia content in ppm down here on the stripped water to prove that we're doing what we're supposed to be doing. And we can show the H2S content up here. Now, one thing I'd like to point out to you is that we've got a lot of H2S in this stream. Now, if you start to think about it, is there any way that we can remove or reduce the content of H2S in this stream? And if you think about it from a pure kind of mass balance point of view, the answer is no. There's nothing that we can do in terms of how we operate this column that will reduce the H2S content. Any H2S that enters the ammonia stripper is going to be stripped necessarily in order for us to meet our bottom specifications. If we're hitting 10 ppm in our stripped water, that means that we're basically going to have to strip all of the H2S that comes into this system. So any H2S that's in this bottom stream is going to end up in this overhead stream. So when we start talking about reducing the H2S content here, it all comes down to how we operate this column. And so our goal in this column is going to really be to maximize the H2S recovery into the overhead while meeting that process specification. And right now, it seems like we're doing a pretty good job. We've got about 93.4% of the H2S that's going into this column being recovered into the overhead stream. The only way that we can reduce the H2S content here, apart from using a scrubber, which we'll discuss in just a moment, is to reduce the H2S content coming in here. And this actually ends up being a fairly non-trivial thing to do. We've got to balance a couple of different things. If you think about what are some of the parameters that we have to play with, we've got three, really. We can play with the column pressure, we can play with the wash water flow rate, and we can play with the reboiler duty. Let's go ahead and start thinking about how we could explore that a little bit more. We're not going to have a lot of time to get too in depth with it today. Like I said, we're going to save the optimization of this for a future course, but just kind of thinking through what are some of the tools that we have available in ProMax to analyze this. I would suggest that the most powerful tool we have available to kind of analyze how the system behaves is the scenario tool. So if you haven't used the scenario tool before, it's a really useful tool. It integrates into Microsoft Excel and it lets us create parametric studies. So if I wanted to create a quick little scenario tool run here, just to get a taste of what exploring this process might look like, I could click up here on Add Excel Workbook. This is going to embed an Excel workbook in my ProMax project that will open with ProMax, close with ProMax, and save with ProMax. And what I might want to do is study how the system behaves under different process conditions. For instance, I might want to see how the system behaves at different boil-up ratios and at different wash water flow rates. So right now, and actually I'm just going to call that wash water flow. Right now, my boil-up ratio, again, is 0.15, and my wash water flow rate is, if I go back here, 3 cubic meters per hour. What I could do, I could create a scenario where I said, let's look at this boil-up ratio of 0.15, and let's explore different wash water flow rates. And I could even say, let's also consider perhaps a lower boil-up ratio. Or perhaps a higher boil-up ratio would be more interesting to look at. And we'll say, look at those same wash water flow rates. As an output, what I might want to look at is my H2S recovery, my ammonia recovery, and then my ammonia in my H2S. Okay, so these are some performance indicators that I could look at. And what I really want to do here is create a parametric study. I'm going to go ahead and put it in units here, where ProMax runs through those inputs that I've defined and then generates these outputs for me in a table. To do that, it's remarkably simple. I would just go to this ProMax tab, click here on the scenario tool, and then I could add inputs and outputs, and then run a scenario and generate these tables. So let's go ahead and do that just really quickly. We've got time. I'll click Add Variable, and our first input is going to be that wash water flow rate. So I'll say wash water flow here. I'm going to choose Select ProMax Object. This is how we select what we're interested in looking at. And I'll go to Phases, Total, Properties, Standard Liquid Volumetric Flow. So here I'm saying use the standard liquid volumetric flow as an input, and I need to make sure I define which values I want to put into ProMax. So put these cells into ProMax. I'll create another input for the boil-up ratio. I'll choose Select ProMax Project. I'll click my column here. I need to go into my column specifications. I'm going a little bit fast here. Basically, the idea is that we can define our inputs and we can define our outputs and run a scenario. Let's define our first output. That's going to be the H2S recovery. So that is one of our columns specifications that we've created. So I'll go H2S recovery and we'll choose value here. Let's add our ammonia recovery. Again, we've got a column specification for that we can just go and point to. And we say we want the output in these columns. And then let's add our ammonia NH3 in H2S. We'll do that. Make sure we've got the right units, the right cells selected. And now I'm ready to run the scenario. I've set up my inputs, I've set up my outputs, basically just told ProMax where to look. And if I click run, ProMax will actually automatically go through and run the simulation for each of these cases and give us the results in the output. Now, this is a really simple scenario. If we were really doing this, we'd probably want to get, we would probably run a larger scenario and try to get a better idea of what was going on. But just looking at what these kind of initial results are, what we see is that when we go up to a boil-up ratio of, say, 0.16, we're very far off specification. So it looks like, if we were to continue to run these, we would really need to try to increase our wash water flow rate. Now we are getting slightly better H2S recovery, 94%, but nothing hugely impressive. We've gone from 93 to 94, but we've really overshot this. So I'm going to go ahead and go back to what we had before, which was case 2. So I'm going to reset my wash water flow rate to 3, and I'm going to reset my boil-up ratio to 0.15. Another thing that might be interesting to think about is the column pressure. The idea here for the H2S stripper is that we are operating at an elevated pressure. What operating at an elevated pressure does is allow us to operate at an elevated temperature at well, and it changes the phase behavior. Operating at that elevated pressure and elevated temperature, it gives us the ability to do that split between H2S and ammonia. But is that 7.9 bar that we're using the optimal pressure? I mean, what if would 7 bar be better? If 7.9 bar is good, would it be good to operate perhaps at a little bit higher pressure, maybe 8.5 bar? And we could take a look at that as well. One practical constraint to increasing the pressure is going to be the temperature that the reboiler operates at. So if I look at this reboiler right now, the temperature here in stream 6, it's about 167 degrees Celsius. Now we need to think, where is the energy for the reboiler coming from? It's probably coming from steam. So let's go ahead and add the steam side of this reboiler and see what kind of steam we would need. I'm going to take a heat exchanger and put it here. If I can get it rotated. And this is going to represent the steam side. Okay, and we'll come over here and we'll say the composition is going to be pure water. And under properties, we'll say that the temperature is, we'll leave the temperature blank. We'll say the pressure is, let's try with low pressure steam. I can never remember what temperature low pressure steam is. So we'll say 3.5 bar gauge and 100% vapor. And then we'll come out to the outlet stream. We'll say 0% vapor, and we will set a small pressure drop. Now, if I execute this, notice that my reboiler turns yellow. And if I open it up, I see there's a warning here. I've got a negative temperature approach. The problem is that low pressure steam, it doesn't have a high enough temperature for that reboiler. Remember, we were at 166 degrees Celsius on the process side, and so we need our steam to be higher than that. So let's try going up to perhaps 10 bar gauge steam. That gets us up to a temperature of 184 degrees Celsius. That's more sensible, but this is going to be one of the bounds on how high of a pressure can we operate the column at. We're going to be limited by the temperature that we can practically get using mid-pressure steam. But now that we've kind of figured out, we could probably go a little bit higher or perhaps a little bit lower. Let's just see really quickly what happens when we make some minor adjustments to the column's pressure. Right now, we are getting an ammonia or an H2S recovery of about 93.4, and we're on spec. So let's see what happens to our H2S recovery if we increase the pressure just a little bit. Let's try going from 7.9 to 8.3. We'll re-execute the column. And interestingly, our H2S recovery has actually gone down. We were at 93%. Now we're at 89%, and that's at a higher pressure. So let's take this back to that 7.9 or 100 psi G. We'll go back to bar. We'll resolve. And by the way, what I'm doing here, taking small steps, this is always advisable when you work with columns and process simulation. Let's try taking a small step down. I took a 0.4 bar step up before, or a 0.5 bar step up. Let's try taking a small step down and seeing if that impacts things. Let's go to 7.4 bar. So if I go back to my specifications now, at 0.4 bar, I've still got a good H2S recovery, but now my ammonia recovery is lower. So I would need to think about increasing my wash water flow rate. I'm actually quite happy with the performance here at 100 psi G, but one of the things to remember is that, again, this is a really complicated system. We've got several things at play here. There's 3 process variables that really strongly interact with each other. The pressure of this column, the flow rate of this wash water, and the reboiler duty here. So this is really a system that's like ripe for optimization. A good way to do it would be to use the scenario tool. For now, what we've got here is a pretty good solution, and I just want to give you an idea of how complicated this system can get if we start to think about adding a wash water column to kind of leave us on a bit of a cliffhanger, okay? So let's say that we did want to wash this overhead stream. Well, what would it look like if we added a wash column? We could take a distillation column, and we could go ahead and give it something like, say, 4 stages. And we're going to try to wash this stream and get down to 1500 ppm of H2S. So let's get that connected. I'm going to go ahead and use some of my recycled stripped water here. And we'll go ahead and just say that we've got a pressure drop here of 0.3 bar. And let's take a look at what the H2S mass fraction is if we add a bit of this stripped water. So let's try to start with 5 cubic meters per hour. Let's see what happens. Okay, so that gave us a pretty significant reduction here. In fact, I'm going to display this in ppm now. And with 5 cubic meters per hour of stripped water, we're able to knock that H2S content down to about 110 ppm. That's pretty good. I can even perhaps think about reducing that. Okay, so now we're at 713, so we're still below that 1500 specification that we proposed. If we get a 3.5, no, we're right about on target. So this appears good, right? But these wash columns can be very complicated because we're going to be capturing not only H2S but also ammonia in this wash column. In fact, if I open this stream here and we look at the composition tab, we see that even though we've captured enough H2S to help us meet our specification, we've also captured a lot of ammonia. And so the next question is, what happens when we think about recycling the bottoms stream from this wash column to the front of the unit? And I'll just show you what happens. And by the way, to do this, what we'll do once this finishes moving is we will add a recycle block to the bottoms. We'll recycle this to the inlet, and what we're going to see is that there's a snowball effect where the wash water from that scrubber that we recycle into the unit, the system tends to snowball. It becomes very difficult for us to get a good H2S ammonia pure or separation in the H2S stripper, and we start to see the amount of water that we need sent to that wash column increase and increase and increase. So again, we're out of time today, so we're not going to be able to optimize this. But I just want to give you a taste of how difficult this problem can be, so that hopefully you're excited about attending a potential webinar where we discuss how to actually get this thing working in August. So I'm going to mix this back with my feed. We're going to get this all connected. And now, if I go through, if I solve my column, let's go ahead and just solve the flow sheet here. And this is going to take a few more iterations to converge. And now what we see is that we are off specification on our H2S here, and we're off specification on our ammonia here. So we had a really nice simulation, and adding this wash column has just hugely complicated things. And now we've really got 4 variables that we have to think about tuning, and they all affect each other. It's a very, very nonlinear system that's very difficult to control and to understand. And so really what you need to do here is either use the scenario tool to help kind of generate maps of the surfaces so that you can understand how the system behaves, or another option would be to use some kind of nonlinear optimization protocol. And I'm actually using a beta version of ProMax 6.0 right now, and that's one of the features that we have added to ProMax 6.0. If you look up here, we've got this optimization tool, and I'm going to click on that and just kind of show you what it looks like. What this tool lets us do is create an optimization case where we create an objective function. In this case, for the sour water stripper, our objective function would probably be to minimize the reboiler duties. And then we can add variables to our optimization case and we can add constraints. And so, here the variables that we would add, we would take a look at optimizing the wash flow rate here, the wash flow rate here, perhaps the column pressure, perhaps the wash column pressure. We would add all of our different process parameters that we wanted to adjust to our variables here. And then we could define some constraints. And our constraints would be whatever process specifications we wanted to have on our overhead ammonia content and our overhead H2S content. So we could set that up and run that. So that's actually what we're going to be doing in a future webinar, is we're going to be optimizing this process using both the scenario tool and the optimization tool, seeing what that looks like. And so I hope that kind of gets you interested. I'm looking forward to when we come back to this in August. And that's all we have for today. First question I had from Jelle is the feed normally not always equimolar in H2S and NH3? Not necessarily. Sometimes it is equimolar, sometimes it's not. It really depends on what units it's coming from. There's a question, what thermal model should we use for the sour water stripper? Again, we're using the electrolytic ELR package for that. How accurate is the result on the ammonia content in the H2S gas? It's extremely accurate. The sour water stripper results that you get from ProMax are very, very accurate. I can personally vouch for them. I have matched many sour water strippers to operating data, and you can trust them on a ppm level, absolutely. Can we get desired specification in a single column? If yes, then why is two-stage preferred? So again, two-stage columns are preferred because they let us produce a separate ammonia and H2S stream. There's a question, is there effect of the feed pH on the overall separation, efficiency, or the reboiler duty? And I would say yes, absolutely. The feed pH is definitely going to affect how the unit performs. We have to think about this in terms of the electrolytic chemistry. I'll pull that slide back up. If you're operating at a low pH, that means that you have a large concentration of protons. That means that you're going to have a lot of the product present for the H2S reaction. That's going to tend to shift the H2S reaction to the left and promote H2S stripping. On the other hand, if you have a high pH, it's going to tend to promote ammonia stripping. So yes, the pH will absolutely affect the performance. There's a question, is ProMax able to predict and calculate salt desublimation in vapors? And the answer to that is yes, that there is a new analysis that we have that can be used on vapor streams to calculate desublimation. So let's go ahead and take a look at it here in Stream 11. So if I open Stream 11 and I go to the Analyses tab and I click Add Analysis, I can add a salt deposition analysis. And here I choose the salt that I'm interested in. So in this case, I would be worried about ammonium bisulfide. And if I click Solve here, I'm told that ammonium bisulfide would deposit, in this case, at 2 degrees Celsius. And so it seems like that 85 degrees Celsius that we're using here is sensible and realistic. So that's the answer to Jelle's question. Can ProMax predict and calculate the salt desublimation in vapors? Yes. And this salt deposition analysis is really intended for vapor streams. For liquid streams, in water streams, my understanding is no. The correlations that are used in this analysis are not intended for use in aqueous phase streams. So this is just for the vapor phase. There's a question, is it possible to replace both recycle blocks with a single block on stream 14? That's a good question, and that's a really good insight. That's something that you should always be looking at trying to do. Get rid of as many recycle blocks as possible. But in this case, I don't think we could do that, because if we had a single recycle block here on stream 14, oh, actually, yeah, I think that might work, because we would still be able to solve this. And if we could solve the H2S, yeah, I think that would work, Barber. Or let's go ahead and try doing that. I'm kind of curious now to see if we could do that. So if you want to make this kind of quick on-the-fly changes, I just made a copy of stream 14. I hit Control-C and then I hit Control-V. And I'm going to take a recycle block. I'm going to put it here. I'm going to use stream 14's copy as the recycle block's new outlet. And let's try to hook that up and let's test this theory. I think that's actually a really good idea. Take this recycle block off. And we'll put this here. No, it wouldn't work, in fact. You could put this recycle here, but the problem is we wouldn't be able to solve the H2S stripper if we didn't have this recycle here. So no, unfortunately here we do have to have 2 recycles. But one of the nice things is, honestly, this recycle on the stripped water converges extremely quickly. And the reason for that is because there's very, very little variation from iteration to iteration because we're carefully controlling the ammonia content. So whenever this block is iterating, every iteration it sees essentially the same flow rate, the same concentration, and the same temperature because we've got these heat exchangers. So this recycle block is really not a problem for us at all. It's super easy. This recycle block's the one that's hard to converge, and there's no way to get rid of it. The question, is it possible to run a dynamic simulation? No, unfortunately, at this point, ProMax is steady state only. How close to real plant results are the ammonia and H2S recoveries? Very, very close to real plant results. As I said, this process is licensed by Bechtel, and Bechtel is using ProMax when they simulate this process, when they're licensing this process. And so what I would kind of suggest to you is, our experience is that the results are very, very accurate, match plant data very closely. And ProMax is also trusted by, the primary licensor of this process, Bechtel. You can definitely have good confidence in the results. So there's a question from Jelle. He's seen a unit with acidification of the first column and then caustic addition for the second column. You can absolutely model that in ProMax. The electrolytic package in ProMax is completely general, and the effect of any acid or base that you add in this system, whether it's caustic, whether it's phosphoric acid, whether it's HCN, whether it's phenol, whether it's mercaptans, will be captured and accurately simulated. And in terms of whether that's part of the Bechtel design or not, I'm actually not sure. I'm not an expert on what their specific current state-of-the-art version of this process is. There's a question about whether you could use fuel gas stripping. You certainly could. You could try to use fuel gas stripping. I think that the challenge that you would have with using fuel gas stripping would be figuring out whether that fuel gas was going to be problematic in your overhead stream or not. Would you want that fuel gas to end up in your SRU? Would you want that fuel gas to end up in the overhead of your ammonia stripper? I have not seen this process used with fuel gas, but what we looked at, to be honest, there are many, many different ways to configure this process. There are many ways to route the wash water, to route the feed water. There are lots of different ways that people make minor tweaks and adjustments and optimizations to this process. Today, we kind of started with the simplest version possible. Okay, well, if anybody has any more questions that they want to ask, you can email me, or you can email one of my colleagues and we'll get back to you. I hope you found it informative. My goal today was really just to show you, if you've got ProMax and you've got a really simple process description, it doesn't take much longer than an hour to really get a solid starting point for work. And other than that, I hope everybody enjoys the rest of their day, and that you guys have a good week. Bye, everybody.